So, let us start this lecture with a thought process from Sir Arthur Stanley Eddington, who says that if someone points out to you that your pet theory of the universe is in disagreement with the Maxwell equations, then so much the worse for the Maxwell equations. If it is found to be contradicted by observation, well, these experiments do bungle things sometimes, but if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. So, that is the sacrosanct of the second law of thermodynamics. That means he is having so much of faith on the second law of thermodynamics, which we discussed in the last lecture. And if you look at, we are having two statements we have made for the second law of thermodynamics. One is Kelvin-Planck statement, which says that it is impossible to have a cycle operating device to absorb certain amount of heat from the thermal reservoir and does equivalent amount of work. That means what? It has to reject certain amount of heat. Without that, it is not possible to have a cycle operating heat engine. And just opposite of that, being made by the Clausius, that is Clausius statement, which says that it is impossible to have a cycle operating device to absorb the heat from the low temperature sink or a thermal reservoir and just transfer the same amount to the high temperature thermal reservoir without any external work, right. It is not really possible. And we have seen also in the last lecture that both the statement are same by, of course, deduction method, right. We first prove that, consider that one is wrong, and then you find out that other is also not correct. So, by that way we have found out, and beside this we have also looked at that certain definitions of what we call efficiencies, like what we call first law of efficiency, thermal efficiency, basically first law of thermodynamic efficiency or first law efficiency. And then we defined also certain performance parameters for refrigeration and heat pump systems, right, that is coefficient of performance, right. And if you look at this COP of your what you call air condition or the heat pump, we do use that as a performance parameter instead of the thermal efficiency, which is being used only for the heat engine. And if you may consider that heat pump we use in the winter season, right, to maintain the room temperature at a comfortable level by extracting heat from the ambient, which is at low what you call temperature. So, now will it be cheaper for you to operate a heat pump or the resistance heater what we use in our country, which will be cheaper to have the what you call to have the cheaper options to have more efficient. In other words, it will be more efficient, which will be heater, resistance heater or the heat pump, which will be more efficient. Actually, it is the heat pump. Unfortunately, we do not use it because it is a costly, and the resistance heater is very cheap, means to purchase, right. So, therefore, but however it is very inefficient. So, COP of the resistance heater will be what? will be very low as compared to heat pump. Now, a question might be coming to your mind, is it possible that we can use this air condition as a heat pump during winter season? Is it possible? Is it possible or not? Actually, it is possible. We have already seen that, But then how to do that without really changing anything? So, that also people have devised. I think you can think of how it can be done. You just reverse the process, like, instead of evaporator which is being used for the air conditioner. So, use as a condenser inside the room, and then the evaporator will be outside. So, that is the heat pump. So, what will be, that we have already discussed, right. Now, what will be, we will be continuing to discuss the second law of thermodynamics, and if you look at, we have talked about this perpetual motion machine, right, earlier whenever we are dealing with the first law of thermodynamics, right. And that means which will be generating some amount of work without absorbing any heat from anywhere, that is the thing we have seen, the perpetual motion machine of first kind. So, if you look at any thermodynamic process, right, must satisfy both the first law and second law of thermodynamics, that we have already discussed, right. And any device that violates any of these two laws is basically known as perpetual motion machine, right. Means perpetual means all the time it will be working without absorbing any heat or any energy from somewhere and doing some work, and that we call basically perpetual motion machine of first kind, because that violates the first law of thermodynamics. If you look at, there are several people have approached, particularly in Western country, where the patent is a very big thing, or a mania I call, right. And in our country we are not having any patent. Do you know what is patent? Do you know, any idea? That means if you find out something, you say it is my property, and if somebody will use, he has to pay money. In our country earlier days it is not that. If you have developed something, that is for the society and you will have to give, so that innovativeness can be propagated very easily. People can tinker it and then develop more. So, this is the which we differ, but unfortunately we are following that patent Raj I call. Nowadays we are having several patents, and to self glorification or gratification, right. So, therefore, if you look at lot of patents were being filed in Western countries for this perpetual motion of machine. Even some people have gone high to invest money because they want to make money, so that if somebody is saying something jazzy, this thing, that also. If you look at also where gullible people are being duped by these so called what you call spiritual leaders. Somebody we say that, look, I will give everything without you need to not to do anything. For example, somebody can bring a rasgulla and give you, just like that. So, that kind of story you might have heard, but those are not really possible so far, this first law of thermodynamics. So, there is a perpetual motion of machine of second kind which violates the second law of thermodynamics, right. So, that you call it a perpetual motion of machine of first kind. We state that whatever the amount of heat it will be absorbing from a thermal reserve at a high temperature, it will be basically converting to the totally to the work, and which is not possible. So, let us consider few examples just to say that this is the as usual a steam power plant, right, where it is having a boiler and a turbine and a condenser and the heat pump. And if you look at, this is a closed kind of a steam power plant which produce some amount of work this thing, and some work has to be consumed by the pump to elevate the pressure of this liquid whichever coming from the condenser, right, and some amount of heat is going out from the from the condenser to out, and of course this heat ring. So these satisfy both the, if you look at first law and second law, right. But if we consider somebody has changed this thing, what he has done, he says that instead of boiler where the fuel is being burnt, right. Now what will be, I will be putting something like a resistors, and these resistors which will be heating the fluid, and some steam will be produced, then it can be expanded in a turbine, and then it will go to the condenser and give some amount of heat to the surround coolant, and then it will pump, and this turbine is connected to the pump, right. That means whatever the power is being developed by this turbine is basically some portion, tiny portion is given to the pump to be get operated, right. So therefore there is no problem, and then this turbine is connected to a generator, right. This is basically a generator, right, and then you are getting the net work output kind of things, right. That means whatever it is giving, and then some amount is going to the resistance, and then net. If you look at, somebody has proposed, look, you do this so that once you start this system, then it will go on for, because what is happening from the generator, you are producing some electricity, and that electricity is used to what you call vaporize or produce the steam, vaporize the water for producing steam, and then that is expanded, is going on. Is it really possible? What it violates? I mean, if it is not possible, it will be either violating the first law of thermodynamics or the second law of thermodynamics. So what is violating then? It is basically violating what? First law of thermodynamics. Let us see how. Because if you look at the net work plus Q out. What is Q out in this case? This Q out is nothing but your QL. This is equal to Q out, and that is supplied continuously without any energy coming from somewhere, How can that possible? So therefore, the first law of thermodynamics is being violated by the system, what I have shown here. It may be, somebody might have proposed or something like that. He proposes that is not right, it is not possible. You can quickly, find out, look, it is violating the first law of thermodynamics. So therefore, it is not possible. So let us take another example, like, so that is again the steam power plant will say, and what will say that, as it is, steam power plant, there is a condenser, right, condenser which will be having, some amount of heat will be rejected. So in this case, for example, some amount of heat being rejected here, right, in the condenser. They say, look, it is a wastage, because what we can do, instead of having a condenser, what we will do, from the turbine, I will just directly connect to the pump, right. I can have, let us say, some steam is being expanded in a turbine, and the same fluid I can put into pump and give, right. So that the heat which is rejected out is a kind of a loss, then it can be utilized, right. So that of course it is taking the heat QH from the some heat source, maybe combustors or this thing by burning fuel, or maybe from nuclear, from the solar, any other place we can take this amount of certain amount of heat. So therefore, and some amount of work is done. So it is not violating the first law of thermodynamics. Am I right? Okay. So is it not a good idea to do that, like you just eliminate the condenser and connect directly the turbine to the pump, so that the fluid, after being expanded in the turbine, can be pumped back to the boiler. Because if you know that the condenser, in the condenser something more than 50% of the heat absorbed being rejected, right. It is a large amount of heat being rejected. So, is it possible really to do that or not? Because if some of you could do, it will be a wonderful thing, because so that what will happen, whatever the heat in this case, if you look at, if the heat is coming out and it is not going out rejected. So, if you look at, there is a condenser here and it is 0, right, QL is 0. So, that means whatever heat being being observed by the fluid in the boiler, right, that is being converted into the work, net work. So, that violates the Kelvin-Planck statement. It is impossible to have a cyclically operating device to absorb certain amount of heat and does the equivalent amount of work. That means, in this case QH, right, is equal to W net, right. Of course, if it is so, then into 100% efficiency of, I mean, you can assume that there is some kind of irreversibility or some kind of losses will be there. You can say, look, I can get a, instead of 40% efficiency, let us say if it is 60% heat is being rejected in the condenser, in the condenser, then naturally the efficiency will be something around 40%. Now, instead of 40% in this device, you can get something around 100% ideally, but in reality you can think of getting around 80-90%, which is a good proportion. But however, it is not possible to have this device because the Kelvin-Planck statement is being violated. So, therefore, this kind of machine is known as perpetual motion machine of second kind, which is impossible to have that kind of things. Of course, if you go back to the history, there are several people, who have used some kind of a, their managerial skill and then convincing power to garner some money by making some very, sophisticated device to say that they can do this. And they have also, maybe sometimes successful taking the wing the out money and other things. Sometimes they are also in the jail. So, therefore, be careful about that, and then of course, one has to look at the thermodynamics, second law of thermodynamics, also first law of thermodynamics, to say that whether the system is feasible or possible or not, So, that we have also seen earlier that no heat engine, can have 100% thermal efficiency. That means, if just now we have seen that if the if it is a heat, if a engine is absorbing certain amount of heat from the thermal reservoir and does the equivalent amount of work, then only it will be having 100% thermal efficiency. But however, it violates the second law of thermodynamics. So, therefore, there will not be any heat engine which can have the 100% efficiency, 100% thermal efficiency. So, therefore, now question arises, what is the maximum efficiency that can be achieved by a, of course, a heat engine, right? What is that? How we will come up with that? And generally, a thought will be coming to your mind that it will be possible only if this ideal engine, which will be can provide, maximum thermal efficiency only if the processes are reversible, right. That means, a reversible engine can have a maximum thermal efficiency. So, what is a reversible process that we have already discussed? Let me just again repeat, so that it will be engraved in your mind, that whenever a system and surrounding is interacting each other through the work or the heat, there will be some changes, and and then this interaction will be have say changes both in the system and the surrounding. And if it is reverse back, right, then there will not be any mark either in the system or the surrounding, then only we call it as a basically reversible process. That means, system and surrounding will be coming back to is the original state from where it was started. For example, if the system is interacting surrounding, it was in state 1, it is going to the state 2, then if it will come through the same path and from the state 2 to the state 1, then we call it as a reversible process. As a result, the net work and and heat interactions will be basically 0 between the system and surrounding. Whenever it will go forward and reverse, the net work and heat interaction will be 0. Then only it will be reversible process. So, if a process is not reversible, then we call it as a irreversible process, right. So, therefore, we will be looking at some of the kind of what you call reversible process when it will be occurring. So, we have already seen the expansion and compression with a infinitesimally pressure difference, right. If when there is a kind of a occurring, so therefore, there will be what you call a very infinitely, and the process is quasi steady state. If you look at, if there is a piston cylinder, this thing arrangement, and if we are assuming that this is my piston and there is no friction here, no friction between the piston and cylinder, and this is my gas and it is being this is being expanded. If you are giving heat, then it will be expanding, it will be moving up the piston, it will be expanding, and then the pressure change, whatever it will be there, P minus dP, if it is gas pressure is here, and this dP is very small and there is no friction in between. And also if there is some heat transfer, and that heat transfer will be gradient between this heat source, if there is a thermal reservoir source at temperature something, and that temperature between the gradient between the system and the source or the thermal reservoir is very small, infinitesimally small, then only we call it as a basically reversible process possible, like either due to the expansion or compression or heating or the cooling, this is very essential. That means the gradient is really should be very small, and of course it is not really possible to have that, because all the natural processes are irreversible in nature, right. And but then question arises, why do we look at the reversible process? And also another question comes to our mind, how to recognize a irreversible process, right. Because suppose we say that the reversible processes do not occur in nature, rather irreversible process occur in nature. Now we need to know how to identify the irreversible process. If a process can proceed in one direction only, right, it cannot be reversed back to the original thing, and that violates basically what you call leads to the violation of second law of thermodynamics, because it is possible. We have taken example of hot tea cup, and which will be, and if heat is transferred from the hot tea to the ambient air, you cannot get back the energy or the heat energy which is heat which is gone into the surrounding to reverse back and come back to the T, T from its surrounding. So, therefore, that is kind of thing we know. And reversible process, it is an idealization of actual process basically, it is an ideal one, and it is not really a real one. And in other words, reversible process is really cannot be achieved in real situation or in our day to day practices. So, now question is why we should bother about it, why we will be interested to look at reversible process. If you look at in thermodynamics, we are mostly looking at reversible processes and trying to solve some problems and then look at it, because it is easy to analyze by considering a series of equilibrium states, or what we call it basically quasi equilibrium states, because the actual process we can analyze by considering occurring in a several equilibrium states, so that it is reversible. That way we can analyze, and it is used as a standard for comparing the actual process, because it is like a benchmark, like okay, so one can achieve till that, not beyond it. So, therefore, that helps us to use this as an yardstick to say that look, it can be done with that. So, and as a result we know that is a limit of the irreversible process, right, and that helps in telling like look, if somebody is claiming that this process is possible which is beyond the reversible, like what it could achieve, then naturally it is not, right. So, that we also use in our day to day kind of things. So, for that reason we need to use this reversible process and then work on it. And we will have to also define a second law efficiency. We have already seen the first law of efficiency. Thermal efficiency is nothing but your first law of efficiency, like we say that how much heat you are being utilized for producing the work, right. We have seen that like how much like one can do. But the second law of efficiency, which we will be discussing a little later on, that will tell you what is the maximum one can achieve, or what is the scope for the improvement for a particular system, kind of things, whether it will be possible or not. So, that we will define little later on. So, for that we need to look at reversible processes. And if we know this second law, then we can, what we will do, we will try our best to reduce the irreversibility in a system, so that our efficiency can be improved. And of course, that can be done by using your intelligence and also design methodology you need to develop, right, and then various ways you can minimize the losses or the irreversibilities rather in the process, so that you can improve the performance efficiency, right, of a either a thermal or either a heat engine or a refrigeration or any other system, as a matter of fact. So, this is very essential, like for you to look at in your even life. For example, you might be working, right. So, you are having some kind of a what you call a timetable, a dincharya, jisko life, kind of things. Suppose you will do something in the early morning, then it will mind will be fresh, and if you do in the night, your energy level will be low, so that your mind will be sluggish, you cannot really do that. So, that helps in identifying your what you call irreversibilities or the losses kind of things to do that. So, what I would suggest, you should look at your timetable of your daily routine, and look at how you can maximize your efficiency such that you can utilize the time, and then you can think of second law of thermodynamics for that. So, let us look at irreversible process, because it is very important to look at irreversible processes. There are various irreversible processes one can think of. As I told, the all processes in nature are irreversible, right, because reversible process is basically a myth, like kind of thing. So, what causes a process to be irreversible? So, what are the processes, like what are the causes? We have already discussed, like if you look at, there will be various ones, some of them I am just identifying here. One is friction, right? Friction, and there is a unrestrained expansion and mixing of two gases or more gases, right? It is not the two gases alone, there might be several gases we mixed, right? And mixing of matter at different states, heat transfer with finite temperature difference, right, because if the temperature gradient is more, then the irreversibility will be more. The electrical resistance heating, resistance heating because of your resisting, and then you heat it, that also is a thing. And inelastic deformation, like elastic deformation, basically you can whenever you release the force, that elongation due to the applied force can be come back to the original one where it was having, right. So, elastic deformation actually reversible, whereas inelastic deformation will be irreversible. And of course, the chemical reactions is are occurring, it is not really have to bring them back in the same, following the same path. So, spontaneous chemical reactions, nuclear reactions and other things, like is basically irreversible. Just to I have to given you some of them, even like in your day to day life, this will be the kind of thing one can connect. For example, if you are trying to do the something in a just in the sense very fast you want to do, then you won't really do your things efficiently, or you are doing in a hurried manner, so that it won't really be, you will be dissipating a lot of your mind power for that. For example, like friction, if you look at, all the time whenever we are considering piston and cylinder arrangement, and in a, let us say this is a gas and it is being heated here, right, and then naturally piston will go up, right, if it is heated and it is insulated. So, the pressure will rise, and of course, you can think of some pressure force is being applied here, right, and then piston will be moving up. And we always say that the between the cylinder and the piston there is no friction, right, but now we will consider there is a friction. If the piston is moving, what will happen? It will rubbing, right. If it rubs both the surfaces, there will be some kind of work being expended and converted into some kind of heat. You might be getting this feeling, like suppose I rub these two hands, what will happen? I get some little high temperature, warm kind of things, right. So, in the winter we do, I always rub these things so that we will be getting some more blood circulation, also with the friction we can get this thing, what you call some warm kind of thing. And if some heat being released here, if the piston is moving up, let us say, and now this heat, when this piston is moving down, right, what will happen? Again it will be, is it this heat which is generated can be converted into work? Is it possible? Certainly no. So, then what will happen? Like again more heat will be dissipated, right, because it is a rubbing surface, and that heat being lost, that work which is being utilized there, it is being lost. And that is basically irreversibility. Although it has gone from one state let us say if this is a pressure, like going for here, this is a PV, and this is the process which is taking place here. Let us say you are in state 1 to state 2, right? And is it, if there is a friction here, can I come back in this way? I cannot. So, what will happen? I will have to go in a different path, because there is some heat which is being expended in the, like in the this thing, and while the work also it is different. So, therefore, what you call it is a irreversibility, and that also happens. Suppose you are having friction between your friends or between your teachers and other thing, then what happen? You dissipate a lot of your energy in that. So, that these are the irreversible processes, right, and one has to avoid. Like if you look at, we always try to avoid the friction in our day to day life to be more efficient. So, let us consider some non-quasi equilibrium compression expansion process. If you look at the what you call the first expansion is occurring here, that means this pressure gas which is here, it is being pushing in a very fast, right. That means the pressure, if it is pressure P here, right, and this is P minus dP, and this dP is not 0. For example, if it is something around 200 kilopascal here, and this pressure is basically what? Let us say something 150 dP. I mean, like, and this is something dP is equal to basically 50. That means this pressure is equal to 150 kPa. So, that means it is very, very high pressure, the gradient. So, that is the first expansion, and that we do, like we do particularly nowadays in your life also. We want to expand our business, we want to expand our knowledge at a very faster rate, and we want to have a very higher growth rate, that is the what going on, and that will be irreversible, right, and that will be causing, because it is a faster, anything faster, therefore a lot of stress being generated among the people because of leading a faster life. So, also in the expansion, and so also in the compression. So, if you look at compression, first compression also will be taking place in a very, very high pressure. Let us say P is here and P plus dP, and this dP is very high value, very high values, right. So, therefore, this is again it will be irreversibility will be occurring, although you may assume there is no friction, even though there will be irreversibilities, right. And of course, friction will be there, and therefore, the in the real situation it will be having. But at the same time, if I will say that in actual system I will be using quasi equilibrium, the pressure difference during the expansion is very, very small, then it will be very slow motion, the kind of things which people may not accept. So, but however, irreversibility goes on, and if you go what you call for a either faster expansion or faster compression kind of process. And there might be another where it is basically the irreversible process, that is the expansion, if there is a what you call partition between these two gas, like there is a hole here, there is a hole, right, and the gas will be coming out to the from higher pressure to the lower pressure. So, that what will happen, that there will be sudden expansion and is unrestricted expansion. So, therefore, there will be also irreversibility. That means you cannot take it back, after it reaches the equilibrium pressure, you cannot take it back to the original one by following the same path. So, let us look at some heat transfer problem, like let us say there is a cold drink which is at 5 degrees Celsius, and the ambient temperature, let us say 45 degree, and some amount of heat is being transferred such that the the cold drink which was at 5 degrees Celsius will go to the 45 degrees Celsius, right. That means the what you call some heat being transferred out, and it is not really possible, as I told, that that the heat energy which is being gained by this cold drinks will be really transferred to the surrounding. So, if you look at this is your surrounding which is at 45 degrees Celsius, right, because this is ambient temperature. So, therefore, that is not really possible. This is an irreversible process, because the system can be restored to the initial state, but not the surrounding. Even if we will do that, like we can have by putting kind of things, but the surrounding will be will not be coming to the initial state. So, therefore, this is an irreversible process. So, since the heat transfer can occur only with a finite temperature difference between the system and surrounding, therefore, most of the heat transfer problems will be irreversible in nature, in actual sense, right. So, therefore, I am like reversible heat transfer is basically hypothetical concept because it cannot be established in the laboratory, and if you look at reversible process means delta T is tending towards 0, very very small heat transfer rate, and if it is heat transfer rate is small, then what you will have to do, you will have to increase the surface area to a very larger extent, and then it will take a longer time because the temperature gradient is very low. I mean, if I say, let us say there is a something 0.5 degrees Celsius difference, like is there dT between the system and surrounding, then it will take a lot of amount of time, and also you need to have a larger surface area to make this. Hence, it is impractical and economically not feasible to have a reversible heat transfer, right. It is not really possible to have this. So, let us now look at like when we can call a process to be totally reversible, and it is possible only when there is no reversibilities within the system or its surrounding, right. That means both the system and surrounding should return back to its original state without any marks on it. So, that is really not possible. So, of course, one can think hypothetically only when like process is process occurring in a quasi statically, and there is no friction or a dissipative effects, and of course, the heat transfer is occurring with a very very infinite temperature difference, gradient kind of things. So, for example, like if I take this, of course, this is a hypothetical, nobody will do that what I am showing here. This is the piston and cylinder arrangement, there is a something gas here which is at 25 degrees Celsius, and this gas in the piston cylinder arrangement will be coming in contact with what you call a temperature bath which is at 25.0001 degrees Celsius. It is a very very small, tiny, negligibly small, and of course, there is no friction here, right. In this piston and cylinder there is no friction, right. If you look at no friction here, and it is this is very very 0, the pressure gradient like the pressure difference between system and surrounding is very very 0. So, therefore, one can say that it is basically reversible process, totally reversible, one can assume, because nowhere irreversibility is there, hypothetical. This is an hypothetical situation, not actually, right. And we can call basically the another situation where it will be coming with the 55 degree Celsius a bath, and the same this is, as I told, that other cases what we are considering, this is 0, there is no friction here. However, this system boundary in that, this is maintaining the almost same temperature, right. If you look at, this is your system boundary here, right. I mean these are all insulated, but here the heat transfer is taking place here, and but this system boundary will be basically at 25 degrees Celsius. If you look at this system boundary at 25 degrees Celsius, therefore, it is, you can say, internally reversible process, where no reversibilities occur within the boundaries of the system, right, because the whole system is remaining almost same temperature, a little bit like same temperature. But the this surrounding, which is for this system, the surrounding 25 degree, which is having a very higher temperature, the gradient is higher, therefore it is irreversible process, and this is externally what you call like it is not really possible to have that. But if no irreversible occur outside the system boundary, then we call as the externally reversible process. That means there is no change in what you call gradient is there. So generally we will be considering the internally reversible processes in our systems wherever we are considering, and I will stop over here, and in the next lecture we will be discussing about the reversible heat engine, that we call it as a Carnot engine kind of thing. Thank you very much.